I don't know if you can see my electromagnetism demo here. We have a plasma ball. There we go. So that's all about our fourth state of matter. Let me pull up the assignments for this week. There we go. So this week we had the CER that was due on Monday. That was the electromagnetism one. Then we had the study guide that was suggested but not required. The quiz that was required. I actually haven't pulled it yet, so I'll try to do that today and then post a makeup quiz. And then the Faraday's inquiry stations, those went up on Thursday, probably around 9 a.m. I didn't get them up by 8 a.m. on Thursday. So that is due today by midnight. And then there's an extra credit assignment, which I found fun trying to figure out. So if you have completed the week's work, then you can do the extra credit assignment. If you do the extra credit assignment but haven't done the week's work, then you don't get credit for that. So don't be doing the extra credit if you haven't done the week's work. Today, I want to talk about the two electromagnetism videos that I posted, the phenomena. So we'll start with the floating magnet. Let me see, which word is the floating magnet? And then I'll do the DC motor. So here is my board for the floating magnet. Here's the magnet that I had put in the copper tubing. The magnetic field wraps around. The north and the south poles are at the bottom and the top. So it depends. It might be flipped the other way. But the field lines are going down on this side, and then they're going up, and then they're going back down again. So you can see that it's a changing field depending where you are in relationship to the magnet. So as I drop it down the tube, that magnetic field that is changing, we said that this was copper. You know that copper is a really good conductor of electricity. So as that magnet is falling down the tube, the magnetic field is changing, and that is inducing an electric field. That electric field wraps around the pipe, and that electric field is inducing a force. Using the right-hand rule, we know that the fingers curl around in the direction of the electric field and the thumb points in the direction of the force. So we have the force due to gravity that is pulling down on the magnet. And there's also the force due to the magnetic field, the B, that's a beta. So that's your capital Greek letter, beta. That represents the magnetic field. This is the force. And you can see that that magnetic field is pushing up on the magnet, but it's smaller than the force due to gravity. So we know that it's going to continue to fall because this force is greater than the one pushing up on it. But it is slowing down the magnet. So that's why the magnet floats on the way down. If we were able to induce enough of an electric field in the copper, we could get it to stay in one place. So there are different ways that you could do that. And hopefully you saw that in one of the videos that Mr. Kumar had done. The other phenomena that I wanted to show today was the simple DC motor. So how did the DC motor work that I had shown in the video? Well, by definition, a motor converts electric energy to mechanical energy. So we take the energy from the battery and we make the wheels on the car turn. That's what your motor does. Faraday's law of induction tells us that a circuit with a current induces an electromagnetic field. Okay, so it induces a magnetic field and thereby induces a force that makes the coil turn. So this is the setup that we had for the electric motor. This is the battery. You can see this is a negative side, this is a positive side, and there was a metal post on either side of those with the magnet on top. This is the coil of copper wire that was resting in this metal post that's on either side. And what the way that the current flows, this wire, this coil of wire is covered with an insulator so that the wire is protected. I had to scrape that insulation off of one side of this wire. So let's say the top side of this wire. And I had to do the top side on this wire also. So that means when the bottom side of the wire is touching the metal, there is no current. When the top side is touching it, there is a current. So as it's turning, it's as if the current is turning on and off, on and off. So when the clear side, not the clear side, the coating is clear. When the side that has been scraped clean is touching this metal, there's a current flowing. So our current goes from the battery, positive, up to here, through the wire, and back down to the negative side. That induces a magnetic field. This magnet that is sitting on top of the battery also has a magnetic field. So the electric current has a field line that is interfering with the magnetic field here, and they push against each other, and the wire begins to turn. Now that the bottom side of the wire is touching here, the current is off. So instead of it falling back to the position it was in, it continues to turn. So that's pretty much the idea that all of our devices are built upon, that the current induces a magnetic field which puts out a force, and so then that can make something turn. If it's on and off, on and off, on and off, then it will continue to turn. So that's the idea behind AC versus DC. Alternating current, that's your AC, and DC is direct current, like what you get from a battery. So are there any questions about anything that's happening this week? That's all I have for today. Next week, we will begin waves. And that's what we will finish up with. So you'll have some inquiry stations to do for waves. There'll be a PET lab and some practice problems with waves. And there's also an earthquake assignment that I'm working on for waves. All right, I don't see any questions. So I will be signing off. I see that we have 2 people. I think we had 3 at one point. So have a good weekend. and take care. Bye-bye.